Welcome. This demo illustrates the Intel OSPRay plugin for USD Hydra that we call more simply HD OSPRay. We'll show you interactive up to photorealistic rendering capabilities using the Intel oneAPI Rendering Toolkit. HD OSPRay provides fast preview exploration for compositing and animation, as well as high-quality, physically based photorealistic rendering of USD content. USD, or Universal Scene Description, is an open-source framework developed by Pixar and is now additionally supported by the Academy Software Foundation. Over the last several years, USD has been adopted by many professional content creation applications such as Side Effects Houdini, Autodesk's Maya, and the Foundry's Katana. The USD Hydra rendering subsystem offers a way to connect multiple rendering backends to different front-end applications that use USD, such as USD View, Maya, Houdini, and a growing list of other applications. HD OSPRay connects our open source RenderKit libraries to USD format data through the Hydra API. These libraries include Intel OSPRay, a high-performance geometry ray tracing kernel library; Intel OpenImage Denoise, an AI-based denoising library which enables high-quality interactive preview; Intel OSPRay, a flexible renderer supporting preview and full physically based rendering with scalable performance and fidelity from laptops to connected data center server clusters. OSPRay utilizes both OSPRay and OpenImage Denoise in its workflow. In the near future, we'll be adding USD volume rendering support through Intel Open Volume Kernel Library. In this demo, we're using a set of scenes from publicly available datasets: Benedict Bitterly's Mitsuba scenes, and Matt Farr et al.'s Physically Based Rendering Book version 3. We converted these scenes to USD format. We'll be releasing an updated version of HD OSPRay and contributing the USD format scenes to open source soon after SIGGRAPH, so you can reproduce this demo yourself. Let's start with a walkthrough of an architectural scene from the PBRT scene collection, where we demonstrate scene content interactions as well as the scalability of HD OSPRay on different hardware platforms. To demonstrate the efficiency of our rendering framework, we start with a workstation with an Intel Core i9 processor with 10 cores, 20 threads. We start with a short stroll to the living room. While it takes some time for any Monte Carlo path tracer alone to fully deliver a photoreal result, we enable our AI-based denoiser to provide a high-quality preview of the scene. Using USD, we can directly manipulate the scene and, for example, remove the sofas in the room by altering their visibility. This now looks a little bit empty, so let's turn them back on again. Yeah, that's better. So let's continue our walk through the villa. Let's stop in the dining area. I don't like that white dining table in the background. Let's get rid of it. Okay, let's continue our tour. Wow, this is a nice spot on the balcony to enjoy the view. Here we can see how our AI denoiser is able to robustly reconstruct the glossy interreflections from a noisy input color channel. Next, let's see how RenderKit scales on different hardware. For this, we show a side-by-side comparison of our Intel Core i9 processor setup with a dual-socket Intel Xeon E5 processor with 36 total cores and 72 threads. One feature of HD OSPRay is that it adjusts the render settings, such as viewport resolution and samples per pixel, to guarantee a smooth interaction with the scene. Let's repeat our tour. As we can see on the dual-socket Xeon setup, HD OSPRay is able to render the preview at higher resolution compared to our previously used i9 setup, and the image converges faster. Nevertheless, the user has the same interactive experience as on the smaller setup, with quality scaling based on the available hardware. As before, enabling the denoiser allows the generation of high-quality preview images in a very short amount of time on both systems. In the next example, we're going to interactively change the lighting in the scene. We use the Modern Hall scene from the Mitsuba scene repository provided by Benedict Bitterly. First, we move around a little bit to get an overview of the scene. Again, we make use of our AI-based denoiser to quickly obtain a noise-free preview of the scene. We now move to a position where we can see all the light sources illuminating the hallway. To change the look of the scene, we might first disable the light coming from the door at the end of this hallway. By also disabling the light in the room on the left, we can dramatically change the mood of the scene. Oh look, the lights are on downstairs. I'll check that out later. Again, our AI-based denoiser quickly converges to an acceptable preview of the scene, making it possible to interactively set up the lighting of this scene. Next, we'll show the well-known physically based rendering Volume 3 cover landscape scene being rendered interactively with USD OSPRay's built-in distributed rendering capability, using a 10-server node dual-socket Intel Xeon Scalable processor cluster that we've named Black Panther. We configure Black Panther to use one node for the USD view application and 9 nodes to collectively render each frame. By using image parallel work distribution to render each individual frame across multiple nodes, allows interactive asset exploration that would otherwise be impossible on a single platform for such a highly complex scene. It also enables higher samples per pixel rendering for faster photoreal convergence. Here we will use 4 samples per pixel for each rendered frame. Using USD, we animated the lighting of the scene as well as the camera path to demonstrate large-scale dynamic content. Similarly, we can directly interact with the scene by disabling lights or geometry and directly see the effects live. Rendering the scene is challenging as it contains more than 3 billion instanced primitives and makes heavy use of texture-driven transparency. The massive complexity of the scene can be visibly observed as we walk among the individual blades of grass. The grass in the background is drawn at full resolution without resorting to level of detail approximations. We now walk along the path and make multiple stops to see how fast the image converges when using our distributed rendering framework. We explicitly disable the use of open image denoise to show the fast convergence of the rendering. And that's the end of our demo. Remember, we're going to provide the code for an updated USD OSPRay version, as well as the USD converted files so that you can reproduce this demo yourself. Thanks and have a great day.